All right, y'all. So today we're going to be doing the redox test, part one, no electrolysis. Let's just jump right in. Starting with question one, it says which substance is a reducing agent, meaning which one is being oxidized. If we remember oil rig, oxidation is loss, reduction is gain. So we're talking about electrons here. All right, so which substance is reducing agent, meaning which one is oxidized? Well, we're only really going to be looking at the manganese compound and the sulfur compound. Hydrogen and oxygen aren't really relevant in this. Only ever relevant if we're using hydrogen peroxide, honestly, or producing hydrogen gas, but we're not. So let's start with manganese because it's first. An MnO4 minus. Each oxygen contributes a -2 for a total of -8 because there are 4 oxygens. The overall charge of this is a -1. Therefore, what number plus 8 is -1? A +7. So manganese goes from +7 to a +2. Ooh, looks like manganese is reduced. It gained electrons. From a 7 to a 2 is a gain in electrons. It went down. Therefore, it cannot be manganese. Therefore, our answer is sulfur in the sulfate compound, D. If we want to double check, we can see that SO2, each oxygen is a -2 for a total of -4. Therefore, the sulfur has an oxidation state of +4. Then an HSO4 minus, SO4 minus H, each oxygen for a total of -8. -2 times 4 is -8. We end up with -1. A hydrogen has an oxidation state of +1. So 1 plus some number -8 is still -1. That should be a +6. 1 plus 6 is 7. 7 minus 8 is -1. So it becomes a +6. 4, 2 plus 6 is oxidation because it gained a charge, which means it lost electrons. All right, every single problem following this one is honestly very, very, very similar. So moving on to number 2, which of the following species would sulfur be reduced if converted to SCl2? So which one of these reduces to that? Meaning if it's reducing to become that, well, let's see what it is. Chlorine is -1 times 2, that's a -2. Sulfur becomes +2. So which one of these is going to be reduced, meaning go down in charge? So let's just go through each one. An S2O3 to minus. O3 contributes a -6. It ends up being equal to -2. So we go from -6, we go from -6 to -2. That means the S2s contribute a total of 4 plus. Because if we do 4 plus -6, we get -2. The only problem here is while 4 plus does reduce to 2 plus, we have 2 sulfurs. So we have to divide this by 2. And each sulfur is a +2. So it's not A. I'm going to erase some stuff so I have room. And the second one, H2S, each of the hydrogens contribute a +1, therefore sulfur is -2. Nope, it has to oxidize to become that. And sulfur is 0. Nope, again has to oxidize. So it's got to be D, SO2. If we want to check, oxygen makes it a -4, therefore sulfur is +4. And +4 to +2 is a reduction, reduced. All right. Moving on, how many electrons are needed when the following half equation is balanced using the lowest possible whole numbers? Well, I'm just going to go through. I see that nitrogen and nitrogen is balanced. Oxygen, we have 3. Oxygen, we have 2. I need to increase the oxygen. I don't want to increase it here because then that would change my nitrogen as well. So I want to increase the oxygen in H2O. I will double it because now I have 2 oxygens here, 1 oxygen here. Together that's 3 oxygens. And I have 3 right here, so that's balanced. Cool. Now, if I look through the rest, I have now 4 hydrogens, and 1 hydrogen. So I'll just change that by putting a 4 right there. All right, with all our balances out of the way, let's go ahead and check electrons now. Just gonna erase all my little scribbles. All right, so when we're dealing with charge, we'll look through each one. I have a -1 plus 4 positives. That's a total of 3 plus. On this side, I have a 0 charge. So we have to add 3 electrons. So 3 plus 3 minus makes 0. 3 electrons. Moving on to number 4. I'm going to try and speed up because if we go through this at this pace, this test will take about 4 hours. So I'm going to speed up just a little bit. Titanium 3-phosphate, 2. So the problem here is that we have to know that phosphate is PO4 3 minus. If we have 2 of them, that's a 6 minus charge. So we have to balance out the 6 minus with 3 titaniums. So Ti, sorry, that looks like a subscript. Ti times 3 minus 6 equals 0. So that means that Ti times 3 equals 6. Ti is 2 plus. So titanium 2-phosphate. This number is literally just our oxidation state. Especially with anything in the D level where titanium is, you got to talk about the oxidation state. Which species could be reduced to form NO2? So we're trying to find out, yet again, a reduction. So something that starts with a higher oxidation state than nitrogen in the beginning. So this is a -4. Nitrogen here must then be a +4, or 4 plus. So N2, 0. Nope, it has to oxidize. NO3 minus. Well, that's 6 minus. And then that has to equal -1. Therefore, nitrogen has to be a 5 plus. Oh, ding, ding, ding. 5 plus to 4 plus is a reduction. Our answer is B. Moving forward. What is the change in oxidation state of the oxygen? All right, well, once we have to look at oxygen. In H2O2, that's one of our oxygen exceptions. It's -1. In H2O, it's -2. It's talking about change. That is a -1 change, C. All right, moving on to number 7. A student performed displacement reactions using metals W and X and solutions of salts metals W, X, Y, and Z. The results are summarized in the table below. So for this, we have to remember that if a metal goes into a solution, and there is a reaction, then, therefore, metal is more reactive. All right, so if we just look at this table, we see that X has a reaction in the W. Therefore, X is more reactive than W. This second table where we have no reaction shows us the same thing. X is more reactive than W. And the third one, W does not have reaction in Y. Therefore, W is less reactive than Y. But X, again, has a reaction. Therefore, X is more reactive than Y. Which makes sense because W is already less reactive. So we can just add it right there. Lastly, Z solution doesn't react with any of the metals. Therefore, Z in solution is the more reactive compound or more reactive salt or ion because it did not react with either of the metals. Therefore, Z is more reactive than X, more reactive than W, more reactive than Y. It is Z. All right, what is correct for this redox reaction? All right, I'm just going to start at the top. I'm going to look at MnO2. Mn starts at a 4+ oxidation state to balance with the -4 from the O2. Then goes to a 2+. It is being reduced. All right, the only thing that says Mn is reduced is this one. All right, we're done. Therefore, it's the oxidizing agent, and we can say the same thing about I. I is going to be from a minus to a 0, like 0 oxidation state. It is being oxidized, therefore, it's the reducing agent, A. All right, moving forward. Number 9, what are the oxidation states of oxygen? Well, in its neutral compound, it's going to be one of these two, 0. In hydrogen peroxide, we already said it's going to be -1. So the only thing is OF2. Well, the thing about fluorine is it's very electronegative, more so than oxygen. So fluorine is going to have a -1 oxidation state, but times 2 because we have 2 of them. Therefore, oxygen is going to be +2. Would you look at that? The answer is C. Moving on, in which species does sulfur have the same oxidation state as in SO32-? We've already done this one a few times in different ways, but we'll go through it anyways. This is a -6, and at the end it's going to equal -2. Therefore, sulfur is 4+. So we're looking for a 4+ oxidation state. We've already looked at this compound before. We know that it is going to be 2+. If we want to go through it again, it is, sorry, I'm going to erase. It is a 6- from the oxygen equaling a 2-. Therefore, sulfur is 4+, which seems like it's the same one, but there are 2 sulfurs. That's really important. Therefore, we have to divide this 4+ by 2, and we get a 2+ oxidation state. So moving on, SO4 2-. That is going to be a -8, but we only equal 2-, so sulfur is a 6+. Also not that one. H2S, these now carry the +2. Therefore, sulfur gets to be -2, which is kind of what it wants, but it is not right. The answer must be D, which we can look that oxygen is -2. Chlorines are each -1 for a total of -4. Therefore, sulfur is +4. Moving on to another one of these reactivity chains. If we have the metal reacting with the solution, then the metal is more reactive, more. Therefore, X is more reactive than Y. And the second one, X does not react with the thing. Therefore, X is less reactive than Z. Therefore, Z is the most reactive, then X, and Y. This says increasing reactivity, so we're just going to flip-flop it. So we're going to go Y, X, Z. Turns out the answer is B. Which compound contains sulfur with an oxidation state of 6+? Again, we've done something similar to this before, but we'll go through. O2, all right, that's a -4. The oxygens contribute with a +4 for the sulfur, not A. H2S, that's going to be a -2 because each of these are +1, +1, not B. H2SO3, oxygens are going to make a -6. The hydrogens are each going to make a +1, +1. Well, turns out this guy's got to be a +4 to balance that oxygen chain out. It is going to be C. We can just stop right there. We know we've hit it. All right, moving on. Oh, sorry, this is not +4. We're looking for +6. My bad. It is also not C. Therefore, it's got to be D. Done so many of these, you've missed your oxidation states. Oxygen is -8. Hydrogens are +2. In the middle, we've got a +6 from H2SO4. So it is D, which is correct for the reaction. We got to look at the oxidizing agent, oxidizing agent and the reducing agent. Let's start with phosphorus. Phosphorus starts at 0. In pH 3, phosphorus, counteracting the +3 from the hydrogen, is going to have a -3 oxidation state. Then in the the phosphite ion, we have -4 from oxygen, +2 from hydrogen, a total of a -1 charge. So phosphate's going to be a +1. It goes from both 0 to -3, so it's being reduced, but also 0 to +1, so it's being oxidized. Well, then it's both. It is both the oxidizing and reducing agent. It is both. So D, the only answer that it has both as. Which represents a reduction. So we have to go through each one systematically, but I can already see an answer here. We have SO3, so that means we're going from +6 to SO4 to minus, also a +6, no change. We have Mn2O3, so that's going to be 6 minus, so each of these individually are going to be 3 plus. Going to MnO2, that's a +4. I'm just all willy-nilly with where I'm putting the plus, but it's okay. That's an oxidation. I'm going from -1 to -2. Oh, there's my reduction. It's C. Which equation shows oxygen undergoing reduction? Well, we just saw the oxygen undergoes reduction when we start with hydrogen peroxide. So it's going to be C, again, the hydrogen peroxide. Oxygen doesn't really like to reduce. Or sorry, it does like to reduce a lot. And then once it's in its oxide, the 2- state, it's done, it's happy. Which coefficients correctly balance this redox equation? Well, you have to do it by a lot of different things, but you can do it with charge. First off, we can already look at these answers, and if we want, we can try and balance the oxygens. We know that our D has to be 4 to balance the oxygen. So it's either got to be A or D. Basically, what I did was I looked and I saw 4 oxygens here, 1 oxygen here. I put a 4 to balance it. So we can go with charge or remember our half reactions. Either way will get you the answer. If we go with charge, we notice that if we leave the coefficient as 1, then we have 2 plus minus 1, or 1 minus, and plus 1. Or sorry, let me actually correct that. We now have 8, so plus 8, for a grand total of +9 charge on the left side. On the right side, we have 3 plus and 2 plus. That doesn't work. That's a grand total of 5 plus. So we cannot leave the coefficients for this iron and this iron as 1. Otherwise, it wouldn't work. So it has to be D. The other option here is the coefficients of iron come from the half reaction of manganese. So I can look at manganese, MnO4 minus, reacts to form Mn2 plus. And if I look at this reaction, I realize I have to add 4H2O to balance out the oxygens. Therefore, I have to add 8H plus. That's fine. We know our coefficients for H plus and H2O are 8 and 4 respectively. So that's totally chill. But we have to then look at the charge and realize that we actually create this discrepancy in charges where we have a 7 plus charge here and a 2 plus charge here, meaning that we have to add 5 electrons to the left side. This 5 right here is what's actually going to influence the charge on the iron. As we balance our half reactions, we multiply by the electrons of the other reaction. So it's going to be D5. Which element has the same oxidation number in both species? All right, let's go through this oxidation number once more. C2H4, each H is going to be a 4 or plus total, so each carbon is going to be a 2 plus. And CO2, oxygens are going to be a 4 minus, therefore carbon is going to be 4 plus. No, not A. H and H2O, well, they're each going to be plus 1. H and NaH, ooh, that's a hard one, but sodium's going to win out and become positive for hydrogen to be negative. There's a couple ways to know that. Usually in a chemical formula, they write the cation first, so that we know sodium is going to be the positive one and hydrogen is going to be the negative one. The other thing is this is an ionic bond, and our alkali metals love to be the cations in ionic bonds. In fact, they will never be the anions, ever. All right, so not B. S in SO42 minus in SO3. We've done this one. In this equation, we have 8 minus equals 2 minus. So this has to be 6 plus. Oh, 6 plus. Oh, well, this has to counteract the minus 6, so it's also 6 plus. Well, there it is. See, the last one, hydrogen peroxide, can't be that one again. What can describe oxidation? We know oxidation is loss. Loss of electrons, so it can't be gain of electrons. When we lose electrons, we increase our oxidation number. Can't be that. Oxidation literally comes from the idea that we are forming an oxide or gaining an oxygen. Can't be that. It's loss of hydrogen. So we'll move on to number 19. Which of the following is a redox reaction? Well, let's just check for a redox being a change in oxidation state. So we'll go ahead. Mg starts with an oxidation state of 0. In the reactant side, oh, it has an oxidation state of 2 plus or plus 2. Sorry, let's do 2 plus. That is a change in oxidation state. Well, it's got to be A already. Don't even have to go further. All right, that was paper 1. Moving on to paper 2. So with paper 2, we start off with this wonderful little balancing. And we can just do this by recognizing that first, I'd like to balance the hydrogens because I can tell they are out of whack because we have 3 hydrogens here and only 2 hydrogens here. So to balance that, I'm going to go ahead and put a 2. And when I place a 2 there, the oxygens then become unbalanced. So I'm going to place a 2 on lithium hydroxide. That is then going to unbalance the lithium. So I'll put a 2 on lithium and we are done. 2, 2, 2, 1. There's your marks. Moving on. A 0.200 gram piece of lithium was placed in 500.0 centimeters cubed of water. Calculate the molar concentration of the resulting solution of lithium hydroxide. So each lithium is going to contribute to the lithium hydroxide 1-to-1 ratio. So we really don't have to worry about any conversions here. It's a 2-to-2, but 2-to-2 is 1-to-1. So let's start with 0.200 grams Li. How many moles will that turn into? The molar mass is 6.94 grams per 1 mole. Sorry, no more parentheses. That turns out to 0.0288 moles. That is how many moles of lithium hydroxide we're going to have. So this was 1 mark. The second mark is then we said 0.0288 moles divided by, and they gave us centimeters cubed. We need decimeters cubed. So you can just take 500 divided by 1,000, and that will give us decimeters cubed. Or another way of saying this whole thing is just instead of doing 500 divided by 1,000, doing 0.500. 0. Got to keep our sig figs. And that's going to be a total of 0.576 mole decimeter mole per decimeter to the negative third of lithium hydroxide. And there's your second mark. Moving on, calculate the volume of hydrogen gas produced in centimeters cubed if the temperature and the pressure are both given. So this one's a bit awkward. It says use sections 1 and 2 of the data booklet. Using those sections, you will find the wonderful ideal gas law, PV equals nRT. Here's where dimensional analysis is infinitely useful. And actually, before we even get there, it says hydrogen gas produced. We see that our hydrogen gas, for every 2 moles of lithium hydroxide, we make 1 mole of hydrogen gas. So we have to first do our conversion right here. We see that we have 0.0288 mole lithium hydroxide. We'll convert that 2 mole to 1 mole of hydrogen gas, and we get 0.0144 mole hydrogen gas. All right, now we move back to our ideal gas law. If we go here and we isolate volume because it's asking for the volume, we get V is equal to nRT divided by P. One quick thing is this is going to give you volume in liters, also known as decimeters cubed. We can convert in the end because it does want centimeters cubed. So you really quick get 1 mark for calculating the correct moles. Then you got to plug this in. N is 0.0144 mole. Here's where it gets a little bit iffy. When you are doing these units, you need to make sure you're using the right R, because the wrong R changes everything. R, the gas constant, can be 8.31 joules, Kelvin to the -1, mole to the -1. This has 2 key aspects. One, you can see it's in moles. So that's perfect because our moles are going to cancel out and that'll help us get to volume. 8.31 joules, Kelvin -1, mole -1. The second aspect to this is the Kelvin. Our temperatures in Celsius. You have to make that conversion. 273 plus 22.5 for a total of 295.5 Kelvin. So I'm going to zoom in so I can get it really exact. 295.5 Kelvin. That's our temperature. If you use 22.5, you'll get it wrong because you have to make sure that your units are consistent. All divided by our pressure, which is 103 kilopascals. This is what's going to convert our volume along with the ideal gas constant because we have energy here and convert pressure into volume. So from this, we are going to find that our volume is equal to 300 and oops, I got my numbers wrong. 0.343 decimeters cubed. But if we multiply by 10 to the third, so we can get centimeters cubed, we'll get 343 centimeters cubed. That's our other mark. All right. BIII. Suggest a reason why the volume of hydrogen gas was smaller than predicted. The best 2 reasons are Li was partially oxidized. That would mean it's already reacted. It's not going to produce. The other one is just our Li is impure. Impurities and partial reactions are like what's going to give you all these errors all the time. All right. C, the reaction of lithium with water is redox. Identify the oxidizing agent and give a reason. So let's go back to here. Identify the oxidizing agent. That means the thing being reduced. Well, let's start with Li. Li goes from A0 to A plus 1. That means lithium is being oxidized, therefore it's the reducing agent. Lithium is the reducing agent. Therefore, our oxidizing agent is the other thing, the water. So H2O is the oxidizing agent. And then it says give a reason. Well, you just have to show that you know that hydrogen is reduced. So you can say H plus, it turns into H, which means it gains, or H2 gains electrons. That's good enough. Or if you want, you can even say the oxidation state goes from +1 to 0, oxidation state. Either of those will help you get your mark. All right, describe two observations that indicate the reaction of water is exothermic. It's exothermic. Number one is heat produced. Anything along those lines will work. Number two, the Li melts. And the reason it melts is because heat is produced. The last one is that you can hear sound. The reason that's important is because it's showing that energy is reduced specifically in such, or energy is released in specifically such a way that produces sound. That helps them know that you know that this is exothermic. Energy has to be released for that to happen. Any two of those will work. All right, moving on to our last question, the big one. Iron disulfide, or iron 2 disulfide, has been mistaken for gold. State the full electronic configuration for Fe2+. All right, for this, I'll bring out a periodic table. And I'll just zoom into it as we need. So iron's right here in the D block. So we have to, as we go through, we're just going to go left to right, starting with 1s2. It says full electronic configuration, 1s2. All right, moving across, 2s2. Moving across, 2p6. Moving across, 3s2. Moving across, 3p6. Moving across, 4s2. All the way to iron, 3d6. All right, so here's the thing. This is our configuration for iron, but it's specifically asking about iron 2+. And this is one of those touchy things about the transition metals. They don't like to lose these D block electrons. They kind of get iffy about that, especially because the D block is a lower energy level than the 3D block is lower energy level than 4s, which means it's instead going to lose these. So I saw a really close one that said 4s1, 3d5. And this does account for 2 loss of electrons to try and keep the D at a partial fill. But it's actually going to instead just lose both 4s's and keep that D full. We're going to end up with the instead answer, and I'm going to try and get this so I don't have to rewrite everything. I'm going to lose that, and we're just going to have this. And that is our Fe2+. Again, because those 4s are actually going to be higher energy than 3D when we look at it. All right, moving on. Explain why there's a large increase from the 8th to the 9th ionization energy. So we're actually going to go ahead and look right back at our periodic table. I'm just going to duplicate it. Oh, I didn't want all that writing, but that's okay. All right. 8th and 9th ionization energies. That's a tricky one, and I'm going to move this down just a little bit so we can read it. When we look at our ionization energies, we're losing electrons. So 1 electron, 2 electron, 3 electron, 4 electron, 5 electrons, 6 electrons, 7 electrons. Oh, getting rough. When we lose our 8th electron, we end up with this full outer shell. We become like argon. So our 8th outer electron basically is the jump from our 1s2, 2s2, oh, I forgot my p here, 2p6, 3s2, 3p6, 4s2, 3d6. These are the first 8 electrons gone. Our 9th electron is coming from here. What ends up happening is much like we dropped all the way back to argon on our periodic table, we are losing an energy level. We are going from essentially the n equals 4, and we can pull that one, but now we're at n equals 3. So we've changed energy level. Changed energy level. Another way to look at it, and I think honestly an easier way to look at it, by the way, saying changed energy level will get you the mark, but I think the easier way to look at it is saying that these electrons are very close to the nucleus, while these electrons are very far. And basically you can say that the 9th electron is closer to the nucleus. Nucleus. All right. Well, moving on. Oh, great. I took the text with me too. Well, I can't change it. Moving on to B. Calculate the oxidation state of sulfur and iron 2 disulfide. We can do that. Iron 2 disulfide. Oh, sorry. Oh, my bad. FeS2. So we know that iron has an oxidation state of +2. It says so right here. Therefore, each sulfur is a -1. There you go, -1. That is the worst looking -1 I've ever written. -1. All right. C, describe the bonding in iron. Y'all, this is just metallic. And the word that you were trying to remember that you kept forgetting is delocalized. Delocalized valence electrons around cations. You could say sea of electrons. It's all the same to me, and it's all the same to the IB. This is basically held together by electrostatic interactions. Electrostatic interactions. All right, 22. Oh, this was the last one. Biochemical oxygen demand, BOD, can be determined by the Winkler method. This was in the reading. A student dissolved 0.1240 plus or minus 0.0001 grams of sodium, sodium sulfate, disulfate, to make 1,000 1,000 plus or minus 0.4 centimeters cubed of solution used in the Winkler method. Determine the percent uncertainty in the molar concentration. All right. This one is definitely difficult. In the molar concentration, we are taking this value and this value. We need both of them, and they both have their own independent uncertainties, and uncertainties add together. So we're going to take this uncertainty, 0.0001 divided by 0.1240, which gives us a 0.08% uncertainty. Now, I did multiply by 100 because this is a percent, so that's where I got that. Then we're going to take the other one, 0.4 divided by 1,000, and we get a 0.04% uncertainty. And again, I multiplied by 100 to get that percentage. Then all I do is I take 0.08% plus 0.04%, and I get a total of 0.12%, and that is my answer. When you write out like this, it seems much easier than it is. It really is. You just take the percent uncertainties of each of them and add them. All right, moving to the giant big steps of the Winkler method, which they actually wrote out here. But turns out we don't need literally any of it. Calculate the amount in moles used in the titration. Well, we can figure this out just by going through our values here. We know that we have this much being used. So we have 37.50 centimeters cubed of 5.000 times 10 to the minus 4th mole decimeter minus 3. They give us a molarity and a volume. So this is just molarity equals mole over liter, or in our case, mole over decimeter cubed. So we're going to go ahead and find the moles by just multiplying decimeter cubed. We can do that right here. First, we're going to have to convert 37.5 into 0.37, sorry, 0.03750 decimeters cubed times 5.000 times 10 to the minus 4th mole decimeter minus 3. Units cancel, and we end up with a total of 1.875 times 10 to the minus 5th mole. It's just a molarity calculation. That's it. Deduce a mole ratio of oxygen consumed in step 1 to S2032 minus used in step 3. All right. So here's probably where it's going to take a little investigative work. We have to find our path from oxygen to S2O3. So I'm going to go ahead and take you down it. I see oxygen converts into MnO2. I see MnO2 is used in the next step to produce iodine. I see iodine is used in conjunction with S2O3. So I have a couple mole ratios I'm going to use. I actually love to do this in terms of stoichiometry. If I take 1 mole of O2, I'm going to use our mole ratios to see that 1 mole O2 produces 2 mole MnO2. Whoops, I said O4. MnO2. Then I see that 1 mole right here, 1 mole of MnO2 produces 1 mole of iodine. I'm going to go ahead. 1 mole MnO2 produces 1 mole iodine. I see that 1 mole of iodine produces 2 moles of S2O3. 1 mole iodine produces 2 mole S2O3 2 minus. Cancel out my units, oxygen, manganate, iodine, and I end with, oh, and all the moles too. And I end with 4 mole S2O3 2 minus. So it's a 1-to-4 ratio. Because we start with 1 mole, we end with 4 moles, it's a 1-to-4 ratio. The book did say you had to memorize that. You absolutely don't. I just derived it in the moment. Moving on to D. Calculate the concentration of dissolved oxygen in mole decimeter cubed in the sample. Well, we literally just found out from our previous one that we use 1.875 times 10 to the negative 5th moles of our S2O3 2 minus. The reason I know it's that is because even though we have 1.875 mole Na2S2O3, I know that just dissolves into S2O3 2 minus. We know that because it tells us that they use this, and it is what we call, the sodium is a spectator ion. So then I'm going to convert that to oxygen. I know that for every 4 mole of S2O3, I have 1 mole of O2. I know that because I literally just solved it up there. So I divide by 4. Oh, this was also times 10 to the negative 5th. Did not carry that thing over. Got to carry it over. We get 4.688 times 10 to the negative 6 moles. That's 1 mark. It does, however, say the concentration. If we want concentration, once again, concentration, molarity is mole over volume, decimeter cubed. So how many decimeters cubed of oxygen did we use? 25.00 centimeters cubed. So we're going to divide by 0.02500 decimeters cubed for a grand total of 1.875 times 10 to the minus 4th mole per decimeter cubed. Just going to fix that real quick. Done. That's a second mark. Lastly, E, the 3 steps of the Winkler method are redox reactions. Deduce the reduction half equation for step 2. Step 2. We've seen this before. We have manganese and iodine. We are looking for the reduction half reaction. Manganese here, once again, for the 15th time, is going to be a +4, and it goes to a 2+. That is our reduction. So we're doing the reduction half reaction for MnO2, reacts to form Mn 2+. Again, that is our reduction. We are going from a 4+ to a 2+. That is reduction. We're going to add 2 H2O to balance the oxygen. We're going to add 4 hydrogen to balance out the hydrogen. We have a 4+ here, a 2+ here. We're going to add 2 electrons to balance out the charge, and we are done. That is that. Hopefully this helps. Have a great night.